Good morning, students. Myself Vijay Shankar from IIECE Equipment at Chiprol Engineering College. Today, we are going to discuss about the another type of the sampling technique, flat top sampling, and some examples on the sampling. Okay, in sampling, we already discussed about the sampling theorem and the reconstruction signal, and two are sampling techniques. One is instantaneous sampling and second one is a natural sampling, and now we're going for the another third one, a flat top sampling. See, the flat top sampling is also called as a rectangular pulse sampling. This is also a practically possible method. Why I am saying this is a practically possible method is also means the previously we already discussed about the natural sampling. It is also practically possible, but impulse sampling is not practically possible method. But easy method to get flat top sampling. See here there is a flat top. It shows that here there is a flat top is there for every width of the sample, with the circuit having sampling switches are there, the sampling switch and the discharge switch, and here the capacitor we are using. Across the capacitor there is a S of t, and that S of t is cross multiply, not the cross multiply, is a convolution with the H of t value, H of t, then the output Y of t will get. Okay, means the X of t and the S of t, the given input function X of t combining with the S of t is not the product here, is a convolution between of X of t and the S of t. X of t with S of t is equal to X of t whenever this function is a delta function. X of t is the convolution with the delta function. The same function will get. Any function is convolute with the impulse function, will get the same signal. H of t with the delta is H of t and X of t is the delta with the X of t. So what is the difference between the natural sampling and the impulse sampling here? For the natural sampling, the delta of t is 1 at t is equal to 0. The t is the variables. Now I am taking the H of t, the signals, with the width H of t, the width of the tau is the width is a tau, my dear students here. Assuming the H of t, for these two we can apply the convolution. Any signal, nothing but H of t is convolute with the delta function is equal to, we'll get the same function, H of t only with the tau with H of t. If suppose this is X of t, means you'll get the X of t. Okay, my dear friends. The zero width is a impulse signal, and the tau width we have here in the flat top sampling, and the top is the flat. The natural sampling also the width is the same. It is not the flat, my dear students. Here it's a flat top. All we have it is a flat in the every sample. Okay, it's combined with the original sample of the signal, sinusoidal signal. Understood? Now, during this transmission, a noise is introduced at the top of the transmission pulse in the flat top sampling. During this transmission, whenever if I am combining the flat top sampling, there's nothing but it's a sample with the original signal X of t. During this transmission, the noise is introduced at the top of the transmission pulse, which can be easily removed which can be easily removed if pulse is in the form of a flat top. If there is any, during the transmission, if there is any noise is occurred, the noise is introduced at the top of the transmission pulse, which can be easily removed, if the pulse is in the form of flat top. Okay, this is the advantage here. Hence, the top of the sample are flat. The top of the sample is a flat. That is, they have constant amplitude. They have a constant amplitude. Hence, it is called a flat top sampling, or is also called as a practical sampling, because it is a practically possible method. Natural sampling and the flat top sampling. The circuit diagram having the sampling switch and the discharge switch here. We can call it as a sample and hold circuit. The sample and hold circuit generating a flat top sampling. Using this circuit, it generates a flat top sampling. Okay, when this x of t is a signal, with this, the sample and hold circuit will get a sample with the x of t, then the delta of t will get here. Understood? The width of the pulse is a flat top sampling, and the natural sampling is increased to reduce the transmission bandwidth. The natural sampling is increased to reduce the transmission bandwidth. Here, the top of the sample remains constant, which is equal to instantaneous value of the baseband. So you get the delta function already I explained. Now itself is convolute with the h of t. You'll get the same function h of t with the width of the top. What is that value of y of t? The delta of t with the convolution of h of t is equal to h of t. And what is the delta function? We know the x delta of t, x of t into sum of n is equal to minus infinite to infinite, delta of t minus n into ts. Okay, my dear students. Okay. So actually, the flat top sampling, before it is an instantaneous sampling with the width is a 0, tau is equal to 0 is an instantaneous sampling. That is the first sampling what we have. Here the noise is there. Noise is more, and it is not useful for the practical possible method. So we are not using the instantaneous sampling. We are taking that with the width of the tau, nothing but the pulse width function. Pulse width function. Let here the x of t the function. If I am taking that, it is a y of t is equal to x of t with the convolution of h of t. And this delta function we already know from the impulse sampling. From the impulse sampling, the x of t sum of n is equal to minus infinite to infinite delta of t minus n into ts. And this is also n into ts only, my dear students, when it is a n into ts. Otherwise, you can keep the t only. Applying the Fourier transformation on both sides. Applying the Fourier transformation on both sides. When we can substitute in the convolution. We know one of the property, the time convolution time. The time is convolution means what is the product here? The frequency is a product. So when if I am taking the y of t is equal to s delta of t or s of t here with the convolution of h of t, that delta of t is multiplied with the x of t, the sum of n is equal to minus infinite to infinite delta of t minus n into ts into h of t. Now applying the Fourier transformation on both sides, Fourier transformation of y of t is equal to the Fourier transformation of delta of t with the convolution h of t. What is the Fourier transformation of this function? Y of f or y of omega. what is here? Delta of omega into h of omega, or let us say angular frequency y of f is equal to delta of f into h of f after applying the Fourier transformation. Okay, see, apply the Fourier transformation in the left hand side, you see the y of t becomes a y of f, and in the right hand side h of f with the convolution. Convolution means these two products are the frequencies. So now h of t becomes h of f, and this function we already know, the x of t, the sum of n is equal to minus infinite to infinite delta of t minus n into ts. By using the trigonometric Fourier series, apply the Fourier transformation, we already derived this x of f into, that is a x delta of f is equal to fs into sum of n is equal to minus infinite to infinite delta of f minus n into fs. This is a function we already know. Fs you can write as x of f into, okay, x of f into fs, sum of n is equal to minus infinite to infinite delta of f minus n into fs, because these two are the product now. Okay, my dear friends, we can say that the primary effect of the flat top sampling is an attenuators of high frequency components. This effect is called aperture effect. Okay, we can say that the primary effect of the flat top sampling is an attenuator for the high frequency components. Attenuated the high frequency component. This effect is called the aperture effect. This can be compensated by an equalizer filters with the transformation, or with the transfer the function h equivalent is equal to 1 by the magnitude of f, h of f. And if the tau is very much less than the ts, then h of f is essentially be the constant over the base band. The y of f is equal to h of f, and it is becomes of tau, the 1 by ts is a ts tau. The sum of n is equal to minus infinite to infinite x of f minus k into f of s. Okay, where h of f is a sinc function here. Is only we are taking that actually is no need of this one, the function. We got the g of t, nothing but the convolution function. We can substitute whenever if it is using that y of t is equal to x of t with the convolution of h of t. By using the formula, we know the integral minus infinite to infinite x of tau, or the delta of tau, h of t minus tau d tau. Substituting that x of tau or the delta of tau is equal to this function x of n into ts, sum of n is equal to minus infinite to infinite delta of t minus n into ts, that the t is now here the tau. Okay, substitute this is a tau value, and h of t minus tau, So taking off the functions, the sum of n is equal to minus infinite to infinite x of n into ts, and h of t minus tau and the delta of tau minus n into ts. By using the shifting property, you know, any of the signal x of t naught with the delta of t minus t naught is equal to, we get the same function, the t naught only. Actually, it is the only the t, and any signal is multiplied with the shifted version of the delta function, we get the signal at t naught only. Okay, using that, the sum of n is equal to minus infinite to infinite x of n into ts, it becomes of h of t minus n into ts. Okay, the spectrum now, the g of f or the h of f, now here I am assuming y of f is equal to h of f into this total function as a x of f into 1 by ts sum of n is equal to minus infinite to infinite delta of f minus n into fs. F minus n into fs is multiplied with the h of f, only the function. Finally, the y of f is equal to, here 1 by ts is nothing but fs. The sum of n is equal to minus infinite to infinite. This is a Fourier transformation becomes of x of n minus n into fs into h of f is also multiplied. The final expression for the spectrum of the flat top sampling signal is y of f is equal to fs into sum of n is equal to minus infinite to infinite x of f, my dear students. You know, not the n. X of f minus n into fs. Okay, this is a formula we already use this formula as in the fs is greater than or equal to 2fm and fs is less than the 2fm is aliasing effect here, and it is avoid the aliasing. We are using the fs is greater than or equal to fm function. In that, the fs is the sum of n is equal to minus infinite to infinite x of f minus n into fs. Is totally the x of f. X of f into the h of f. That x of f is the fs into the function. You say here the x of f, the 1 by ts into this function becomes of sum of n is equal to minus infinite to infinite x of f minus n into fs function. Is the equation for the spectrum of the flat top sample signal. Okay, my dear students. Now, you can see the comparison of the various sampling techniques. The three samplings we already discussed in the last class. The yesterday class we discussed about the instantaneous sampling, natural sampling, and now we discuss about the flat top sampling also. What is the first parameter? The principle of sampling is it uses the multiplication by an impulse function. Instantaneous sampling is a multiplication of the x delta of t is equal to x of t with the sum of n is equal to. And natural sampling, it uses the chopping principle. And flat top sampling, it uses the sample and hold circuit. Sample and hold the circuit. And the circuit diagram shown here for the instantaneous sampling with x of t, it's that the switch is there. Whenever the switch is on, the x delta of t is a combined equation of the x of t and the impulse function. If the switch is off, we'll get only the zero signal, the impulse signal here. And the graphical representation of the natural sampling is like this here. It is also switch only. But here the C of t is there. And C of t is equal to 1 and the 0. It depends upon that the value of x of t will get s of t with x of t. Okay. And the circuit diagram with combining with the x of t signal with the width here. There is some width. But upwards there is no any flat response. Okay, my dear students. But here the flat top response for the flat top. Now only we see in the circuit having the sample switch and the discharge switch. X of t here. Here there is a sampling switch and the discharge switch. The circuit, the C, and we can take this as a S of t. This is a circuit using for the flat top as a sample and hold circuit. And the circuit diagram now, not the circuit diagram, the characteristics. There is a flat top. Flat top. after combining with the original signal x of t. Following my students. And what is the realizability here? It is not a practically possible method. It's a very important. And these 2 points, my dear students. The principle of the sampling is a multiplication of the impulse function. And here we are using the chopping principle. And the flat top sample, it uses a sample and hold circuit. Okay. And what is the realizability? The instantaneous sampling is not practically possible method. And natural sampling is used for the practically. And flat top sampling is also used for the practical. And what is the rate here? That tends to infinite and it satisfies the Nyquist criteria. And the noise here, the noise interference is a very maximum here. Noise interference, why it is not the practically, and here the noise, and it is reduces what I said here, the flat top sampling, because of the flat top here is a constant. Due to this, the noise is reduces. Okay, is a minimum and is also the minimum here actually. The noise is introduced at the top of the pulse, which can be easily removed if the pulse in the form of the flat. Here the maximum, not the maximum, my students, is the minimum. Okay, noise interference. And the time domain representation, the x delta of t is equal to the sum of n is equal to minus infinite to infinite. X of t is the x of t, my students. And delta of t minus n into ts is a sampling of all the functions is combined addition. And coming to the natural sampling, we use here the rectangle function. This is a rectangle pulse. The rectangle pulse x of t is equal to tau. This is a tau, my students. Tau a by ts. Sum of n is equal to minus infinite to infinite. X of t, the sinc function. Sinc. Okay. And the last flat top sample, whatever we have here, the sum of n is equal to minus infinite to infinite, fs into x of f, and that function is multiplied with the h of f also after the frequency domain function. You see the frequency domain function, fs into this one, and tau a by ts, and this one is a sinc function is converted from the time domain to frequency domain, and here it is multiplied with the h of f also. This is a h of f. The time domain representation and the frequency domain representation for the both, not the both, but the 3 instantaneous sampling, natural sampling, and the flat top sampling responses. Following my students, the most important point is instantaneous sampling is not possible for the practical method, and these 2, the natural sampling and the flat top sampling, is possible for the practical method. And the sampling rate is infinite in the instantaneous sampling, but the natural and the flat top is a Nyquist rate, and the Nyquist criteria it satisfies, means within the boundary only. Okay, noise interference is maximum in the sampling, instantaneous sampling, and the natural sampling and the flat top sampling is a minimum because of the flat is a very constant in the flat top, and here also comparing with the, it is not the flat, but the width is there. Okay, the C of t van is C of t is equal to 1, and the C of t is equal to 0. C of t is equal to 1 means x of t is multiplied with the C of t to get the s of t is equal. Taking the time domain functions individually from the sampling theorem itself, or the reconstruction signals time domain representation. After applying the Fourier transformation of all these 3 equations, we'll get in the frequency domain, the first one is x delta of t, and second one is s of f, and the third one is also the s of f, because the output here we take the s of t, and here also the s of t. Finally, we'll get the s of f, and here also the s of f. And in this circuit diagram x delta of t, the time domain function becomes frequency domain function x delta of f. The comparison is very important, my students. Now coming to the next one, effects of undersampling. Effects of undersampling. Already we discussed in the last class, but once again, there is some points we have to learn. What is the undersampling effects, nothing but aliasing. When a continuous time band limited signal, when a continuous time band limited signal is sampled at a rate lower than the Nyquist rate, lower than the Nyquist rate. What is the Nyquist rate here? 2 omega. Nyquist rate is a 2 omega, my dear students. Nyquist rate 2 omega. Omega means 2 FM maximum frequency. Nyquist interval means Nyquist interval is 1 by 2 omega seconds. Here it is a hertz frequency. Nyquist rate is a frequency. 1 by 2 omega, or omega is nothing but the maximum frequency. 1 by 2 m, 2 FM. Alright. When a continuous time band limited signal is sampled at a rate lower than the Nyquist rate. What is that Nyquist rate? 2 FM or 2 omega is less than, then successive cycles of the spectrum y of f of the sampled signal y of t overlap with each other. See here, there is a overlap here. Overlap with each other, nothing but aliasing. Okay. Hence, the signal is undersampled after fs is less than the 2 FM and some amount of aliasing is produced. Some amount of aliasing is produced because of overlapping in the undersample of fs is less than the 2 FM. And the next point saying that aliasing is the phenomena in which high frequency component in the frequency spectrum of the signal takes identity of the low frequency component in the spectrum of the sampled signal. Is the definition of the aliasing, my dear students. High frequency component. This is a high frequency component, my dear students. That shows in the low frequency, and this one is a low frequency that shows in the high frequency. This is a high frequency and the low frequency. Actually, it is a high, and actually this is a low frequency. Because of overlapping here, the high frequency component of the frequency spectrum of the signal takes identity of the low frequency component in the spectrum of the sampled signal. Nothing but it is aliasing. The aliasing is the phenomena, the definition, my dear students. Due to the aliasing, it is not possible to recover the original signal x of t from the sampled y of t by the low pass filter. Due to this aliasing, we can't recover the original signal. So by using the greater than and the equal t, the function only, the sampling rate, we can recover the original signal by using the practical low pass filter or by using the ideal low pass filter. Practical low pass filter we are using for the greater than the 2 FM, and ideal low pass filter we are using to recover the original signal for the equal function. Fs is equal to 2 FM. But in this condition, it is aliasing effect. It is not possible to recover the original signal x of t from the sampled signal y of t by the low pass filter. And coming to this one, the signal is distorted and the information signal contains a large number of frequencies. Dividing the sampling is always a problem. See, this distortion occurs after using the low pass filter. It looks like this. Okay. The spectrum looks like this. There is a distortion occurs here because of overlapping. The distortion occurs, but it is not the original signal to recover. The signal is distorted and the information signal contains a large number of frequencies. Dividing the sampling frequency is always a problem. Next point you can see here. The signal is first passes through a low pass filter which blocks all the frequencies above the maximum frequency FH, band limited to the original signal. The low pass filter is called pre-alias filter. It is used to prevent aliasing effect. This low pass filter is called pre-aliasing filter. It is used to prevent aliasing effect. To avoid the aliasing, what we occurred here, the pre-aliasing filter must be used to limit the band of frequency of the signal to FM hertz. The definition, what we are saying, the sampling. What is the sampling definition, my dear students? Once again, I am saying this. A signal which is band limited to the FM hertz, a signal which is band limited to the FM hertz can be completely recovered by the from its samples if the sampling are taken at the rate of see here, the sampling frequency Fs must be selected such that Fs is greater than or equal to Fm. If the samples are taken at the rate of Fs is greater than or equal to 2 Fm. It's a very, very important, my dear students. Effects of undersampling. Okay. In this chapter, you have to learn the main is what is sampling. What is sampling? The definition. And second one is straight and through the sampling theorem. Sampling theorem. And it is derived by using the instantaneous sampling. And 3, briefly explain about the three different sampling techniques. Sampling techniques. And fourth one, effects of undersampling, nothing but aliasing. And fifth one, avoiding different techniques used to avoid aliasing. Nothing but I already told that is Fs is greater than the 2F, and aliasing occurs Fs is less than the 2F. So these are the 5 is very, very important, and the not last and not the least here, the sixth one is the difference between sampling techniques. Okay, now we already discussed this one, sampling techniques. So these are only the topics we have in the sampling theorem, sampling of the 3rd unit for the EEE students, and it is in the 4th unit for the ECE students as per the 19 syllabus. That is a half part of the 4th unit. Okay. Total this, what I am saying here, the total sampling, write it as a assignment, my dear students. I already said that is the properties of the Fourier transformation and the Fourier properties of the Fourier series, and this totals unit sampling. Definitely you get the 3 marks in the part A, and if it is a 7 marks or the 8 marks is there, definitely will get minimum of 10 marks. Very simple, only the 6 questions we have. There is a definition and proof of sampling theorem, different types of techniques, and that difference here, effects of undersampling, what I explained now here itself. Fs is less than the 2Fm is a overlapping occurs here. And how you can avoid this overlapping by taking off Fs is greater than or equal to 2Fm. One time is a greater than, another time is a equal condition. Okay. So totally the 3 topics I given for the assignment, you can write it and hold yours at your side only. Okay. So with this, the completion of the sampling and some examples we have. how we can find the sampling is there. I'll give that examples. Let me go for the examples, my dear students. Until now, we learn only the single tone signals. Single tone signals, my dear students. Suppose if one example, if I take the example here, if x of t having multi-tone signals, x1 of t plus x2 of t plus up to so on xn of t. Multi-tone signals. Actually, x of t is equal to x1 of t is a single tone signals. Here we can call it as ones of multi-tone signals. Okay. Now for n is equal to 2, here the n is equal to 2, we have the x of t is equal to x1 of t plus x2 of t, because I am assuming the n is equal to 2 here. It's a multi-tone only. So more than the 1. The frequency for this one is a f1, let us, and for this the frequency is a f2. Okay. Now, if I am taking the x1 of f, x1 of f with the minus f1 0 here and plus f1 with the frequency of f as of x1 of f, the frequency domain of the first signal. And coming to the second signal, the frequency domain of the second signal x2 of f is having the frequency, maximum frequencies, minus f2 and f1. Okay, my dear students. And this is a band limited, actually the f2 is greater than the f1. It's a band limited of f1 here, the band limited of f2. Comparing these two, f2 is greater than the f1. Okay, my dear students. f2 band limited, the maximum frequency is more, for the maximum frequency for the x1 is more. Okay. Now I am combining the two functions. The combining the two functions means the Fourier transformation of x of f, applying the Fourier transformation is the x1 of f plus x2 of f. Okay. Now can add the two functions to get the x of f, the multi-tone. Individually, the band limited signal for the x1 of f is a f1 and x2 of f is a f2 minus. But this is also f2. Now, what is the band limited for the x of f? Because it's a multi-tone. Individually, we got the x of f is the x of f and the x2 of f, this one. Now, what is the x of f? And these are characteristics for the x of f. Now, I'm adding these two functions. What is the value of f minus f2? Here the 0. So, minus f2. Let us take the magnitude is a2. a2 because here the magnitude is a2 and this one is a1, let us. Okay. And up to that f1, here the f1 is there, minus f2 is a minus F2, is a minus F1, A2 is there. And at the F minus F1, here the A1 and here is the A2. Both we can add the functions. Now the amplitude is A1 plus A2. Get minus F1. Up to the F1 here, plus F1, the amplitude is A1 plus A2. And then at F1 here, and here also the F1 is a 0 and A2. Downside the A2 value, and here the F1 plus F1, and here the F2. A2 is a magnitude, and here also the A1 plus A2 x of F. Okay. Now, the x of t, now it is a band limited as what is the Fs here? The sampling frequency Fs is greater than or equal to 2. What is the maximum here for the combining these two functions minus F2 to plus F2? So 2 into F2. Okay. Is a condition we can use. X of t is band limited to the n is equal to 2. Here, Fs is greater than or equal to 2F2. If it is a n means what is the Fs? Fs is greater than or equal to 2 into Fn, capital N, my dear students. The n value, the Fs, the sampling frequency is greater than the 2 into Fn. It is n is equal to 2, it is a F2. N is equal to 3, it is a F3. Means Fs is equal to 2 into the maximum frequency component present in the x of t. In the case of multitone, what is the sampling frequency? Fs is equal to 2 into, I'm taking the equal to condition, 2 into maximum frequency component. Maximum frequency component present in x of t. What is x of t here? X of t, when the single tone x1 of t and the double tone multitone is x2 of t. 2 into maximum frequency component present in the x of t means is a maximum. Suppose it's the x3 is there, that is a maximum. Suppose x4 is there, that is a maximum. So on the xn is a maximum. Follow my dear students. In any given signal x of t having the multitone, what is the sampling frequency? Fs is equal to 2 into the maximum frequency component present in the x of t. Maximum frequency component present in the x of t. I assume here the n is equal to 2, so whatever the maximum frequency is there in the x2 of t, that is a minus F2 and the plus F2, that is a sampling. Fs is greater than or equal to the 2 into F2. Okay, my dear student. That is one example for the multi-tone signal. And next example, you can see, second example, example 2, x of t is equal to sine 2 pi into 100t. Okay. 2 pi f, my dear student, it is sine omega t. So actually it is equal to sine omega t. What is the omega? 2 pi f. 2 pi f into t. What is the f is given here? Nothing but the maximum frequency is 100 hertz. 100 hertz. And what is the time period? 1 by t, 1 by the frequency is 1 by 100 is a 0.001 or is a 10 milliseconds. 10 milli I usually here. Milli means 10 power minus 3. Okay, here the 10 power 1. Minus 3 plus 1 is a minus 2 and 1 by 100. 10 milliseconds. The time period is a 10 milliseconds. If SS is greater than or equal to 2 FM, the sampling frequency is, assuming that 400 hertz. What is the sampling time? Is 1 by the 400 is equal to seconds. That is a 2.5 milliseconds. Okay. The Fs is a greater than or equal to 2 FM. If I am assuming the Fs is 400 hertz, the sampling frequency is a 400 hertz. What is the sampling time? Sampling time is a 2.5 milliseconds. Okay. So the characteristics here for the sinusoidal function. So I am using the positive and here the negative is also there and the negative and the positive. The 0 and here is a 5 and the maximum frequency, nothing but the sampling frequency, is at the 2.5 and this is 7.5 and here the 10. So totally the time period of the full cycle, if I am assuming here up to the full cycle, is it 10 milliseconds. This is x of t, the sine signal, the milliseconds. Okay, my dear students. 10 milliseconds and the Fs you can assuming that as 400 hertz, the time period, the sampling time period is a 2.5 milliseconds. So 2.5 and again it is a 7.5 and so on. The totally the time period is a 10 milliseconds. The number of samples per cycle. The number of samples per cycle is how many samples we have here in between? The 1, 2, 3 and the 4. The 4 samples are there. N is equal to 4. How many number of samples we have per cycle is 1, 2, 3 and is a 4 total. Following my students. That is x of n is equal to x of t and that sine function, how we'll get it find n is equal to 4 means suppose x of n is equal to x of t and it is t is equal to n into ts, the sampling time, and the t is equal to n into what is the time sampling period? Time period here is a 1 by 400. Okay, you can substitute in the sine 2 pi 100 into t. T is nothing but n into ts. N, what is the ts here? Ts is equal, t is equal to n by the 400. By the 400 minus 4. Is a 200 and denominator having the 400. Sine pi by 2n. Okay. Sine pi by 2 into n. Because the 2 into 100 is a 200 and becomes here the 200. Now the fundamental period is, what is the fundamental period? Saying that n is equal to 2 pi by the omega. Is a fundamental period when n is equal to 2 pi by omega. What is the omega now? Omega is equal to, see, when sine pi by 2 into n is equal to sine omega t, then you can assume sine omega n, because here sine pi by 2n, converting into the discrete function. So sine omega n. What is the omega? Nothing but 2 pi f into n, sine of. And pi and n we have, 2f is there. Okay, equal to 2f is equal to 1 by 2. And f is equal to 1 by 4. Okay, actually you have to see that it is a n is equal. What is the omega? Omega, instead of omega, is equal to pi by 2. Okay, you substitute here the 2 pi by the omega when comparing of these two functions. Omega is equal to pi by 2, and pi get cancelled. In the denominator 2 will get here. N is equal to 4. Okay, that is n is equal to 4. Following my students. So what is the conclusion for this? What I am saying here? We already know the x of f is equal to, or x delta of f is equal to fs into sum of n is equal to minus infinite to infinite. X of f minus n into fs is a single tone equation. Oversampling is fs is greater than 2fm. In this case, we get God band and fs minus 2fm. And third equation, fs is equal to 2fm. It is called the Nyquist rate, and it is a reconstructed filter is using ideal low pass filter. And coming to the fs is less than the 2fm, undersampling, aliasing effect or folded error. And coming to the fifth one, multi-tone signal. What is a multi-tone signal? Saying that fs is equal to 2 into the maximum frequency component present in the signal to be sampled in the x of t. Actually, maximum frequency component present in the signal x of t. In the multi-tone, the sampling frequency is selected as the frequency component present in the sampled version of the signal is given by fn, f2, and so on. The fn, fs is greater than or equal to 2 fn. And the sixth point, after this totally the conclusion of the with examples, when the x of t having the signals x1 of t, x2 of t, and so on, xn of t, the multiplications, fs is equal to 2 into sum of the frequencies. When the product is there, the time domain function. Coming to the frequency domain function, fs is equal to 2 into sum of the frequencies. Sum of the frequencies. So that is equal to fs is equal to 2 f1 plus f2 plus so on fn. Okay, my dear students, any signals is given. See, in the previously x1 of t, x2 of t, and so on. In this, the function is 2 into maximum frequency component present in the signal. Suppose the given signal x of t having x1 of t into x2 of t into x2, x3 of t, and so on. What is the frequency component? What is the frequency component here? That saying that fs is equal to 2 into sum of the frequencies f2, fn, and fn. Whenever the signal given the x of t is equal to x1 of t into x2 of t and so on xn of t, the time domain function, in the frequency, the fs is equal to 2 into the sum of the functions, means f1 plus f2 and so on the fn. This is a sampling frequency. Okay. The previously we learned, if suppose the x of t is equal to x1 of t plus x2 of t plus and so on xn of t, what is the sampling frequency? fs is equal to 2 into fn, or the 2 into maximum frequency component is a maximum frequency component present in the signal x of t. Whatever the signal here, the maximum is a xn of t on. That frequency not directly taken is xn. Here also the not directly taken the xn value or frequency of that signal. If it is a product of the signal is given the 2 into the sum of the frequencies f1 plus f2 plus so on. And the third one, if x of t is given, that signals is a convolution. x1 of t convolute with x2 of t with the convolution of x3 of t and so on, xn of t. If the signals, we see that signal having the sum, signal in the product, and now the third one is a signal in the convolution. What is the maximum frequency? The sampling frequency, the 2 into minimum of f1, f2 and so on, f1. Okay, the opposite to the product of this time domains. Minimum is what is here? The x1. This 2 into f1. fs is equal to 2 into f1. Okay, whatever the minimum value, the minimum frequency in that. And now the last one, the number of samples per cycle, n is equal to 2 pi by the omega. The number of samples per cycle, the fundamental period, you can call it as a fundamental period. N is equal to 2 pi by omega, or x of n, the discrete function, converting of the time domain function, substituting of n is equal to n into ts. This is a very, very important, my dear students. In the signal, the first one also. Signal is a product, the 2 into the sum of the frequencies. Signals in the sum, the sampling frequency fs is equal to 2 into the maximum frequency component present in the signal x of t. And the signal having the convolution, the sampling frequency is a minimum of the f1, f2 and so on, fn. If it is a minimum here, the f1 is there, that is 2 into fn. And what is the fundamental period for the given any samples per cycle, that is n is equal to 2 pi by omega, where x of n is equal to x of t, with t is equal to n into ts. Okay, using these formulas, in the tomorrow's class, we can solve some more examples. Okay, my dear students. By tomorrow, I can conclude the third unit of for the triple E and fourth unit, half part of the fourth unit for the ECE students. By tomorrow, we can conclude the third unit, my dear students. Okay, some more examples. See in the tomorrow's class. Any doubts? Please rise. Okay, thank you.